This is Chapter 8, High Power Switching, and we're looking at Triacs and how we can add the new component Diacs to improve that circuit slightly. So first off, a couple of issues with Triacs, just so that we have a reason to improve them and add the Diac in. The first issue is the heat dissipated in switching on. So remember, for our BJT, we've got a graph that looks like this. So this is the off region, this is the linear region, and this is the on region. Now the linear region is the problem, and that's where we get heat dissipated, because we have both a voltage flowing and a current flowing, which means we've got power. Now, because the capacitor charges slowly, we can take some time to pass through the linear region of the triac. Now, triacs don't have a massive issue with this. It's not a very big linear region, but it is something we would try and avoid ideally. So ideally, we would want to go from off to on instantly without any crossing through a linear region. The other issue is the variability in the switch on point. So remember the graph that we looked at when we looked at triacs, and this is the supply voltage. Let me just do a different color. And this is the triac, so that's off. Hit the trigger point on, hit the trigger point on, hit the trigger point on, and so on. So this is the on region, and this is the off region. Ideally, obviously, this is 0 because we have no linear region. And the other issue for triacs is that we have a slight variability in when this threshold value is. And there's two reasons why we have a variability in this value. First one is temperature. Triacs are quite sensitive to temperature, so you're going to get, even a few degrees, you'll notice a slight difference, which can be annoying because obviously this then affects the phase angle because it was turning on sooner or later in the cycle, which therefore affects the power to our output component. It is also because triacs are mass-produced and they're not very precise. So there is quite a bit of variation between different triacs. Okay, so enter the diac. Now the diac is quite like a triac. It still has two main terminals, and the graph looks very similar. Notice though that this is a breakover voltage, not a switch. There is no gate on this. It's effectively two Zener diodes stuck together. So this region here, it is off, it is not conducting, and then suddenly we hit the breakover voltage and we zoom across and we are on and we are conducting this region here. So that is a diac, and it's basically a Zener diode, but it works in both directions. So it's got a breakover in both directions. So how do we add this in? This is how we add it in. We put it on the gate. So we put the diac here on the gate between the snubber. Remember, the resistor and capacitor are called a snubber. You don't have to memorize the word snubber for the exam, it's just a nice word. And the gate of the triac for triggering it. Now, how does this deal with the two issues we talked about? Well, you will set your breakover voltage to be much higher than the threshold voltage so that you can mask the issues. You're not going to be going like hundreds of volts higher, but you might have a threshold voltage in theory of, say, 12 volts. This is AC, so remember you could be talking up to 240 volts RMS. So you're talking large values here because it's AC. So the threshold value might in theory be 12 volts, in which case the diac might well be set to have a breakover voltage of, say, 20 volts, so significantly higher. What this means is we've got no point where it's in the linear region. It's either on or it's off, because the diac won't conduct until we've reached 20 volts, which is well over the switching threshold for the triac. So straight away it goes from off to on, and then when it turns off, again, it's instantly on or instantly off, which means that we are not dissipating much heat at all in the linear region, so in the triac. So it's efficient in that sense. The other advantage and the other way that we deal with the issue is the variability switch on. Well, the Diac is like a Zener diode. They are much more precisely manufactured. So if I say we're going to get a Diac with a breakover voltage of 20 volts, it will be 20 volts. It's not like the variability in the threshold voltage for the Triac. And that's it. All of the graphs and stuff, obviously, that we looked at last time do apply to this circuit, so you do need to know those. The only real difference we're adding in here is the Diac and these two reasons why it improves it, and you may well need to know this graph as well of the Diac. It could come up on the exam. So do make sure you've drawn the circuit and memorized it, and all of the graphs associated with Triac stuff in general. That's it for high power switching.